Welcome back to ChemDoctor. In this particular video, we're going to do more practice with heterogeneous equilibria, and in particular, for this example, I'm going to work with a common precipitation reaction that normally is done in the laboratory as part of qualitative analysis. So here's the setup. We're going to take a molar equivalent of lead nitrate, a solution of lead nitrate, and we're going to combine that with a molar equivalent of potassium iodide in solution so that all of the lead and all of the iodide is reacted. Now, if we write the complete balanced equation for this, this is what it's going to look like. So we're going to have lead nitrate, and this is a classic precipitation reaction, so that means we're combining a solution that contains lead nitrate with a solution of potassium iodide. This is a double replacement reaction. It's quantitative, meaning that if there is an equilibrium, it lies so far to the right that the reaction essentially goes to 100% completion. We're going to form lead iodide, which is a solid, and that's where the equilibrium issue is going to come in. So I'm going to go ahead and underline this. And we're going to produce a new solution, which consists of potassium nitrate. Now, we can write the net ionic equation for the formation of the lead iodide, and this is what it's going to look like. The way this problem was set up, we produced quantitative amounts of the lead iodide. Now, when you do this in the laboratory, this is what it's going to look like. You combine the lead nitrate with the potassium iodide, and if we did it in a beaker, keep in mind that the way I set the problem up, we've got molar equivalents of these two things. So in terms of the balanced equation, one lead ion reacts with two iodides to produce 1 mole of PbI2, and we have provided exactly molar equivalents of these two things. So we have formed, in the initial precipitation reaction, we formed 100% of this compound from what we put in to the system. So there's no remaining lead ion and no remaining iodide. It's all initially in this form. Okay, now what this is going to look like in the beaker, if we did this in a beaker, is the lead iodide forms a bright yellow precipitate. I don't know if you can really see this. I think I'm going to have to, I want this to be yellow, but I'm afraid it's going to look more, it's going to be, okay, that's not really working. So it's a bright yellow PPT, or precipitate. Okay, so bright yellow precipitate. So the lead iodide is going to be a bright yellow solid, PbI2. All right, now, where does the equilibrium calculation come into play here? So basically, lead iodide is a sparingly soluble salt. So this is a saturated solution. In the solution, we've got, sitting above it, we have K plus and NO3 minus sitting above the solid. But sparingly solid, saturated solution, what that means is that some of the lead and some of the iodide is dissolved in the solution above the solid, but very little of it. So I'm going to rewrite now my equilibrium expression for this. Remember, because this is a heterogeneous equilibria, that the lead iodide in the solid form is actually not part of the equilibrium expression. And we have an equilibrium constant for this we call a KSP. All right, which stands for solubility product. So sparingly soluble salts immediately form saturated solutions. Some of the lead is in fact dissolved in the solution above the solid. Some of the iodide is as well. But by comparison to the potassium nitrate that's in here, there's very, very, very small amounts of the lead ion and very small amounts of the iodide. Now, the equilibrium constant for the formation of the lead ion and the iodide in this case is 9.8 times 10 to the minus 9th. Now, what we're going to do here is we're going to calculate the concentration of lead ion and iodide at equilibrium. So how do we accomplish this? The first thing I'm going to do is remind you that the amount of the solid here doesn't matter. As long as there's some present, the density of the individual solid is going to remain constant throughout any changes in equilibrium that might occur between the lead ion and the iodide. So these two guys right here are the only things that are going to be changing if we manipulate equilibrium. All right, so these are going to be the important aspects of this equilibrium. Now, the concentration of the solid here doesn't matter, but what I'm going to do to set up our ICE table is I'm just going to define the concentration of the solid as A, and I'm going to let A act more or less as a placeholder, so maybe I'll put a parentheses around this. And initially at equilibrium there's going to be 0 of this and 0 of this. So this would be the situation immediately after mixing the lead nitrate and the potassium iodide together. And then once the solid forms, then equilibrium would be established, producing a very small amount of the lead iodide, or excuse me, of the lead ion, and a very small amount of the iodide. So we can show that transition this way, where the A is going to decrease by an X value. And again, let me remind you of stoichiometry. We have 1 mole of lead iodide that's going to produce 1 mole of lead ion, which is going to produce 2 moles of iodide. So A is going to decrease by some very small value in X. Lead ion is going to be produced as a function of X, and the iodide is going to be produced as a function of 2X. Now we can set up our equilibrium expression. So KSP equals concentration lead ion times concentration iodide raised to the 2nd power. So plugging in, we're going to have 9.8 times 10 to the minus 9th. That is going to equal X for the lead ion, and it's going to equal 2X for the iodide, quantity squared. So now, simplifying, we're going to have 9.8 times 10 to the minus 9th, and that is going to equal X times 4X squared, which is equal to 4X cubed. All right, now dividing both sides by 4, we're going to have X cubed is equal to 2.45 times 10 to the minus 9th. All right, now we're going to take the cubed root of both sides. So X is going to equal 0.0013. Now, this reaction I'm going to stipulate occurred in exactly 1 liter. So the molarity is 0.0013 molar. All right, now that's going to be the concentration of the lead ion. and the concentration of the iodide will be 2 times that value. So the iodide concentration will be equal to 0.0026 molar. Okay, and once you get, the way teachers do this is different, or professors. Normally when I teach equilibria, and then when I get to heterogeneous equilibrium and I finish the chapter on equilibrium in general, then I go straight to solubility products and equilibria that's focused on sparingly soluble salts. So I actually do it right away rather than waiting. So you may encounter this later, or you may encounter it sooner. But what we just found here is basically, between these two values, is basically the solubility of lead iodide in its saturated solution. So this is a type of equilibrium that deals specifically with saturated solutions and sparingly soluble salts. All right, and with that, I'm going to go ahead and close this video.